Hello there, welcome back to Star Stuff, where you know I'll be stating facts, but you never know how I'm gonna say it. In this case, my how is in the form of a human person called Simon Dan. Dan, how's the hat going? I mean, how are you doing? Thank you for doing this with me.
You just had to go there, didn't you? Hello everyone, pleasure to be here.
In today's video, with the help of Simon Dan, I'll be starting off this series explaining the hard to understand stuff, with a topic that many of you brought up as something that is not often fully understood.
It's gravity and everything it affects. Let's explore this.
First of all, let's break down what gravity actually is. At its simplest, gravity is modeled as a force that pulls things with mass toward each other. That's anything with mass. You, your phone, your teacup. The more massive something is, the stronger its gravitational pull, which is why Earth pulls you down, the moon pulls the oceans, and the sun basically runs the entire solar system. Now, with our focus in space, let's look at how gravity affects the planets, moons, and stars. Gravity is the reason why space isn't just random chaos. It's organized chaos. Much better. Planets orbit stars because gravity is constantly pulling them inward, while they're moving sideways fast enough to miss. So instead of falling into the sun, they fall around it. The same goes for moons orbiting planets. It's basically the universe's most elegant game of
"You can't catch me, no, 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 no."
Looking beyond the solar system, galaxies, like the Milky Way, are held together by gravity. Billions of stars, gas, dust, and something mysterious called dark matter that we can't see, but definitely invited itself to the party. Without gravity, galaxies would just drift apart, like a group chat after drama. Now we have the drama queens themselves, black holes. These are regions where gravity is so strong, not even light can escape. Get too close, and you're not just pulled in, you're eventually spaghettified. Yes, that's a real term. No, it's not comforting. It's also known as the noodle effect. It only happens when the gravity pulling on your feet is significantly stronger than the gravity pulling on your head. Asteroids and comets are in space too. They're the small guys, constantly being bossed around by gravity. Their paths are shaped by the pull of planets and stars, which is why they don't just wander off, like confused space tourists.
Okay, let's drop down a level of scale and talk about the Earth and the physical effects that gravity has on its atmosphere and oceans. And the most basic of these is the fact that gravity gives our atmosphere weight. We don't usually think of air as heavy because we move so easily through it. But the atmosphere we all live in isn't weightless. Every molecule in every gas in our atmosphere is being pulled down by Earth's gravity. And that in turn creates air pressure. That's what air pressure actually is. It's the weight of the air above you pressing down. And that is precisely why pressure drops as you climb higher. If you go up a mountain, that means there's less atmosphere above you, which means less weight pressing down, which of course means a lower air pressure. Therefore, the atmosphere is densest nearest the surface and less so higher up. That is a direct physical result of gravity. This one fact explains a lot of things when it comes to our atmosphere. It explains why aircraft need to have pressurized cabins, why weather balloons expand as they rise, why water boils at lower temperatures on top of mountains, and why your ears pop when you take off or land on a plane. All of these things happen because atmospheric pressure changes with altitude. And atmospheric pressure changes with altitude because gravity gives the atmosphere weight. Now, flat earthers will often say things fall not because of gravity, but because of density and buoyancy. Of course, density matters, nobody's denying that. But density alone does not create that intrinsic down direction. That direction has to come from somewhere. And this is the problem with relative density. As we've already discussed, the atmosphere gets less dense as you go higher. That means the air just below an object is very slightly denser than the air above it, which means by the relative density crowd's own logic, there should always be a net upward force. Everything should slowly drift upwards. To further prove relative density wrong, let's consider the atmosphere itself. If it were true, we would expect the gases in the atmosphere to arrange themselves into layers, with the densest gas at the bottom and the lighter gases stacked in layers above in order of their density. This would mean, if that happened, there would be 75 meters of gases before you reach oxygen, with everything below that being mostly argon and carbon dioxide. So unless you were stood at the top of a 20-story building, you would not be breathing. But what about the oceans? Gravity has obvious physical effects on that too. The oceans are not simply stuck to Earth. They are massive bodies of water being pulled towards Earth's centre under gravity, giving them weight, creating water pressure and defining sea level. The deeper you go, the higher the pressure becomes. This is of course because deeper water has more water above it. Now this is measurable, it's predictable, and entirely caused by the weight of water in a gravitational field. Again, density plays a part here too. Saltier water is denser, as is colder water, and those density differences drive ocean currents. But they do not replace gravity, they operate within it. But of course, one of the clearest effects of gravity on Earth's oceans is the tides. Tides are caused mainly by the moon's gravity, but the sun also plays a small role too. Now, the moon pulls more strongly on the side of Earth facing it than it does on the Earth's centre, and more strongly on the Earth's centre than it does on the side facing away from it. That difference in gravitational pull stretches the ocean into tidal bulges. As the Earth rotates through those bulges, voila, we have tides in coastal areas.
Just when you think gravity is simply things falling down, it becomes a full-on, reality-bending magician. So gravity doesn't just pull objects, it bends space itself. According to general relativity, which is the geometric theory of gravitation, massive objects warp space-time, like placing a bowling ball on a trampoline. Now imagine rolling a marble past it. The marble curves inward. It's not because it's being pulled in the traditional sense. It's because the surface itself is curved. Light does the same thing. Even though light has no mass, it follows the curvature of space-time. And that's how we get gravitational lensing. Light from a distant galaxy bends around a massive object. That object acts like a cosmic lens, and we see distorted, stretched, and even duplicated images. Sometimes we even get full rings of light called Einstein rings, which is a phenomenon that occurs when a distant background galaxy aligns behind a massive foreground object, which is proof that the universe just likes to show off. Gravity doesn't just mess with space, it messes with time too. The stronger the gravity, the slower time moves. This is called gravitational time dilation. Near something massive, like a black hole, time slows down dramatically. So if you hung out near a black hole, not recommended, a few hours for you could be years for someone far away. Now, if we zoom in on a subatomic scale, looking at atoms and particles, gravity technically still exists. But compared to forces like electromagnetism, it's basically irrelevant. The electromagnetic force between two electrons is trillions of times stronger than the gravitational attraction. So while gravity dominates planets, stars, and galaxies, at the tiniest scales, it's completely overshadowed. Physicists are still trying to reconcile this mismatch, which is why gravity is at the center of one of the biggest problems in physics: quantum gravity. How do we combine quantum mechanics with gravity? The short answer, we don't know yet. The long answer, we really don't know yet.
Now, it's all well and good talking about space and light and the Earth, but something that is much harder to hand-wave away is the effect that gravity has on life itself. Gravity is built into how living things grow, function, and survive. Take plants, for example. Roots always grow down, and shoots always grow up every single time. Plants are actively detecting the direction of gravity and responding to it in real time, a process called geotropism. Now, plants sense gravity using specialized cells. These cells contain dense structures called statoliths. These settle at the lower point of the cell, signaling which way is down. The plant will then distribute a hormone called auxin, and it does so unequally in response to these settled statoliths. In the plant's roots, auxin will accumulate on the root's lower side, and that inhibits cell elongation. This means the upper side of the root grows faster, forcing the root to curve downwards. In stems, the auxin again accumulates on the lower side, and that promotes cell elongation. This causes the lower side to grow faster, which means the stem will shoot upwards. And get this, in microgravity environments, like the ISS, plants do not grow in neat up and down patterns. Roots and shoots drift in random directions because they don't have Earth's gravity to respond to here. But we can do one better here. What about you? What about the human body? Your body doesn't just exist in a gravitational field, it actively detects it. Inside your inner ear is the vestibular system. This includes tiny fluid-filled structures and small calcium carbonate structures called otoliths. And these otoliths shift in response to gravity. Now they then press on sensory hairs depending on your orientation, and that constantly tells your brain which way is down. That's how you can tell your position or movement when you've got your eyes closed. Again, if we refer to our astronaut friends on board the ISS, their inner ear structures don't have a consistent direction to respond to. Because of this, they often suffer from things like disorientation, motion sickness, and loss of balance. And if you think about it, your body is constantly fighting gravity. Your heart pumps blood upwards against gravity to reach your head. Your veins have valves to stop blood pooling in your legs. Then you've got to think about your posture and movement, requiring constant muscular effort to resist gravity. If you take gravity away, life doesn't just behave differently. It loses its sense of direction, its strength, and its structure.
Let's expand a little on the idea of orbiting. An object in orbit isn't floating. It's in constant freefall. Take the International Space Station. It's being pulled toward Earth by gravity, but it's moving sideways so fast that Earth curves away beneath it. So it keeps missing the ground forever. Atmospheric drag is what slows it down, leaving the astronauts inside feeling weightless. And this isn't because there's no gravity. It's because everything is falling together, so nobody hits the floor. Getting something into orbit isn't random. You need the exact balance between speed, altitude, and Earth's gravity. Too slow and it falls back. Too fast and it leaves Earth entirely. Which sounds cool, until your satellite, which was intended for Earth's orbit, suddenly becomes an interplanetary explorer.
And what about how we use gravity to our advantage by steering spacecraft through the solar system? In 1977, Voyager 1 and 2 were launched with a mission to explore the outer planets. But the thing is, they didn't carry enough fuel on board to fly directly to each of those planets. What they used instead was gravity itself. As each spacecraft approached a planet like Jupiter or Saturn, it fell towards that planet under gravity, accelerating as it got closer. Then, as it passes the planet, it's flung back out again, but now with a new direction and crucially a new speed. This is called a gravity assist or a gravitational slingshot. Make no mistake here, this is precision navigation. The trajectory of each flyby has to be calculated very carefully. Come in at the wrong angle and you can either hit the planet or miss your next target completely. Get it right and you can chain multiple flybys together, which is exactly what Voyager 2 did, using gravity assists from Jupiter, Saturn, Uranus and Neptune. And those maneuvers aren't guessed, by the way. They were calculated years in advance. Engineers knew exactly where the spacecraft would be, how fast it would be moving, and how the planet's gravity would bend its path. And of course, it all worked. Decades later, both Voyagers are still sending back data from interstellar space, following trajectories that were mapped out using nothing more than our understanding of gravity.
So gravity isn't just a force. It's warping space, slowing time.
Barely noticeable at tiny scales, but somehow helping us explore the universe. And we're still trying to fully understand it.
Thank you all so much for watching, and a huge thank you to my friend Simon Dan for helping me out with this video. Dan, I bet you won't be able to guess what my next topic is in the series.
Well, given the series is called Explaining the Hard to Understand Stuff, is it about why Simon Dan would dare believe that he could outbet star stuff? I mean, I was finding that hard to understand when I was wearing a hat for an entire video the other day.
So close, but no. You're just gonna have to find out what it is next week. If you enjoyed this video, please like and subscribe. and let us know if you have any questions in the comments. Cool beans!